Lenz's law. It's one of the important laws considered in this chapter, electromagnetic induction. This law speaks about the current induced in the process. This law says that induced current is always produced in such a manner that it always opposes the main cause, which was responsible for its production. Listen again. The induced current is always produced in such a manner that it opposes the main cause producing it. For example, I'll illustrate with the help of these two examples here. You see, north pole of a magnet is being taken closer to the coil. Now, coil is experiencing the approach of north pole. And because of the north pole, the magnetic field or the flux, you might say, that is entering the coil, this will also increase with its movement. The main cause is being here approach of north pole. How shall it be opposed? If it is repelled, then only you could say that north pole's approach will be obstructed. In order to approach the north pole, another north pole is needed over here. So here one north pole should be produced. And what will happen? Anti-clockwise current will have to be developed over here. Anti-clockwise current, then only north pole will be produced. This you might remember, north N, and this shows anti-clockwise direction. Similarly, see here the south pole is being taken away from a coil and the main cause is recession of south pole. How could it be opposed? By just attracting it backward. Who will attract the south pole? North pole. Again, north pole is needed in this coil, and for that anti-clockwise current needs to be produced again. When north pole approaches or when south pole goes away, in both the cases, you will find that anti-clockwise current is produced. In the same manner, you could decide when north pole is taken away or even south pole is taken closer to the coil. Second thing is eddy current. Eddy current is also known as Foucault current. You see, whenever the magnetic flux changes through a conductor, many small current loops are formed like this. Current loops are formed inside the conductor and these are responsible for producing heat. Now, how could it be saved? How could you just reduce the process of getting or producing eddy current? The only idea is that you laminate the whole conductor, means one conductor has to be sliced this way, sliced. Once you slice, once you cut this, or you just split into laminas, you see between two laminas there is going to be air and air is insulated. Now this air is going to obstruct the production of current. So soon as the conductor is laminated, you have reduced the possibility of production of eddy current. So this is one way. And second thing is by introducing the insulators within the laminas, insulators oxides or ferrites, these are better insulators. You introduce, you see the whole transformers, entire transformers world works on this principle. We try to minimize the production of eddy current there simply by using these insulators. Even sometimes oils are also used as insulators within the laminas. Then uses are given separately: induction meter, brakes of electric trains in melting the metals, diathermy, a process of treatment, speedometer, and in deadbeat galvanometer, this eddy currents principle is used. And finally, now we are heading towards the production of induced EMF when the conductor will move in the field, and for that we are to study Fleming's right-hand rule. You see, we have already completed Fleming's left-hand rule. You might remember father, mother, child, force, magnetic field, current. Fleming's left-hand rule, force, magnetic field, current. Similarly, It's Fleming's right-hand rule. One similarity will make the whole thing very simple. In both the rules, this stands for magnetic field. Index finger represents the magnetic field in both the rules. And in both the rules, the middle finger produces or represents the current. So these two are similar. If you have remembered this Fleming's left-hand rule, obviously you have done 2/3 of this Fleming's right-hand rule also. The index finger representing magnetic field, middle finger representing induced current or the current. Now, what's difference is that in the case of this thumb only, here it was force, magnetic force in Fleming's left-hand rule, and here in Fleming's right-hand rule, thumb is going to represent the motion of conductor. So, what is Fleming's right-hand rule? This will represent the magnetic field. This thumb is going to represent the motion of conductor. Then middle finger will represent the direction of current induced. Listen again, this is Fleming's right-hand rule, whereas this is Fleming's left-hand rule. Magnetic field, current, force, motion of conductor. Fleming's right-hand rule.